And the question that I would like to ask is, what is the probability of finding a particle whose wave function is given by this object between x1 and x2? So what's the probability that I perform a measurement on the position of the particle and the outcome is between x1 and x2? So that's the question. Quantum mechanics can give me an answer to this question, and I can determine the probabilities. How do I do that? Now this wave function is the complete prescription of the particle. It is the complete description of the particle. So the probabilities must somehow be computed from this wave function. So now what I would like to do is, I would like to compute this probability. The probability capital P of performing a measurement and having an outcome x between x1 and x2, right? So this is the probability that my lies in a certain range, the outcome lies in a certain range. That does not mean that the particle was in this range, by the way, but it's just the outcome of a measurement given my wave function psi xt. So I would like to find out this probability. This is the question that I would like to ask, and I would like to yield an answer to this question. As human beings who are experimenting with nature, this is the best we can claim to. This is all that we can know. What's the probability that the measurement outcome yields a value between x1 and x2? Now, how do I find out this probability from the wave function? Everything must lie laden inside the wave function. The wave function must give me the recipe or the ingredients to find this probability. So what I do is, let me draw a zoomed in view of that particular region of the wave function. So x, remember, is a continuous variable here. Remember this term, continuous variable. X can take up an infinite number of values. And I am interested in finding the probability of locating the particle between x1 and x2. So what I do now is that I divide this region. Is the wave function constant in this region? No, it's changing. So what I would like to do, I would like to divide this region into small intervals. So I divide this into a large number of intervals. This is one interval, the next interval, the next interval, the next interval, and so on. And this region, which is my region of interest, is subdivided into smaller and smaller subregions. Let me focus on one region. Please don't talk to me. Please. Now this is a small region. It's the ith region inside this interval. So this distance is xi. So this location of this point is xi. And the width of this interval is xi plus some width of the ith interval, delta xi. Okay, so this width is delta xi. Now don't confuse this with uncertainty. Now if this region is small enough, I can assume that the wave function is constant inside this region. Because the wave function cannot change wildly, it has to vary smoothly. It's impossible to have a discontinuous wave function. That's not allowed by quantum mechanics. So wave functions change smoothly. So if my interval delta xi is small enough, I can assume that this wave function is almost constant inside this interval delta xi. So now I would like to find out the probability of finding the particle in this green shaded region, in the ith region. Likewise, I find out the probability of locating the particle in each one of these small regions and add up the probabilities. Probabilities just add up. Alright? So now I've subdivided my problem, my domain, my range of interest into smaller subintervals, and I determine the probability of locating the particle in each subinterval. Okay? So now the probability of finding the particle in between xi and xi plus delta xi. So this is an interval, and the probability of locating the particle inside this interval is given by the value of the wave function in this interval psi xi, the value of the wave function at this interval. Now if this interval is small enough, I can take the value of the wave function in the middle of this interval or at the boundaries of this interval. But since this interval is really small, I'm assuming that the wave function is constant within this interval. So I'm actually assuming that the wave function is like a staircase. It remains constant within each interval. Okay, this is my logical assumption here. So what I do is I find the value of the wave function in this interval psi xi at some time t, and I take the modulus squared of this, and I multiply this with the length of the interval, delta xi. So this is the probability, this object, this number, this expression yields the probability of finding the particle as a measurement outcome in this narrow thin region of space. And it's given by the modulus squared of the wave function, which is a complex number at this location xi, multiplied with the width of the interval. Okay? So now what's the total probability of finding the particle between x1 and x2? I have subdivided this range into a large number of small intervals. So the probability of locating my particle in this entire range is going to be approximately equal. Approximately because I'm making this assumption that the wave function is constant within each interval. It's going to be given by the sum over all i's of this sum over all i's. Let me write it on a bigger area. So the probability of locating my particle in a narrow regime is approximately given by the sum of the value of the wave function at a particular point inside the interval modulus squared delta xi, which is the width of each subinterval, and I sum up over all possible intervals. Suppose I have capital N intervals, a large number of them. So this is my probability of locating the particle within this region between x1 and x2. Is it possible to make this approximation exact? If I make the interval smaller and smaller and smaller, my approximation approaches exactness, exactitude. So I can make these green intervals smaller and smaller, which means that I can reduce each delta xi. So I can make the resolution of my instrument finer and finer. What this means is that if I were to make delta x, if I take the limit that delta xi, each one of them goes to 0, smaller and smaller, then this approximation will become an exactitude. And this summation can then be written as an integral. That's the meaning of an integral. So what I could do is, instead of this delta xi, I could write dx, a small interval x, this magnitude squared just remains like it previously was, and this yields the result. And if my x goes between x1 and x2, this integral will give me the probability of locating the particle as a result of a measurement between two extreme values. So what I've done here, I have converted an approximation which involves summation over finite intervals. I've converted that to an exactitude which involves an integral over infinitesimal intervals. Infinitesimal means exceedingly small, vanishingly small. I break up this interval into finer and finer and finer intervals, so that I'm sampling the exact wave function at each point. And since I'm sampling the exact wave function, this approximation becomes an equality. This is actually how an integral is defined. This is the meaning of an integral. This is the physical interpretation of integration. But from this formula, you also recognize that this, on the left hand side, we have a probability. And on the right hand side, we have a length. Dx has dimensions of length. So what should this object have? What should be the dimensions of this object here? क्या होंगे इसके dimensions? आप बताएं? जी, आप बताएं? क्या होंगे dimensions? नहीं, इस ऑब्जेक्ट के क्या dimensions होने चाहिए? आप बताएं? जी, आप प्लीज. What are the dimensions of this object? What are the units of probability? No units. So what should be the units of this quantity? No units. Alright. So this is a product between two quantities. What are the units of dx? Length. Dx is measured in units of length. So what should be the units of this quantity? 1 by length. So this should be the probability per unit length. Alright? Probability per unit length is called probability density. So this object, just this object, I can write this as a small p. Probability density, the function of position and time, and it's defined as the modulus squared of the wave function. So the wave function, if I take the modulus square, I get the probability per unit length. This is an interpretation of the wave function. This is how an abstract quantum field, which is hard to measure, which cannot be measured on its own, steps into the classical realm of making measurements. So as classical beings, we are always making measurements with our instruments of quantum systems. And we get certain measurement outcomes. For example, we have a voltmeter. On a voltmeter, we have a scale. This scale is fitted with a needle. This is a measurement device, and the outcome is the position of the needle of the scale. This is what we will do as human beings, as experimenters of nature. This is what a physicist really is. So we only have access to measurement outcomes of experiments. So there's a probability that the needle will lie in this position, and a probability that the needle will lie in another position, and the probability that the needle will lie in another position. And the wave function tells us what are the probabilities that the needle lies between these two decimals on the scale. What's the probability that the needle lies between these two gradations on the scale? That probability per unit length is derived from the wave function, and it's not the wave function, it's the modulus squared of the wave function. So the probability density is given by the modulus squared of the wave function. And if I were to, is this a real number? You've done a full-fledged homework on complex numbers, so this is a real number. And probabilities, which are classical outcomes, they are real numbers. And it all makes sense. And if I were to write this in an alternative fashion, I could also write this as psi complex conjugate multiplied with psi itself. This is the modulus squared of a wave function. So this is how I interpret the wave function. And the wave function gives me probability densities. And if I would like to find out probabilities, I would like to make this integral. Let me give you another example. One example, and I have one homework problem in homework number 2 that actually discusses this kind of argument. So for this free particle, what will the probability density look like? I give you 2 minutes to think over this. I have this wave function for a free particle. What would the probability density look like? So what I'm interested in is here I plotted, say, the real part of the wave function. Given this real part, the magnitude or the amplitude is A. Could you please draw on your notebooks what the probability density function will look like, given this wave function, this one. Doesn't matter, yes. Doesn't matter. For this particular wave function, it's valid for all times. But just take any point in time. That's the wave function. It's a complex number. Remember, the wave function can be complex. In this case, it's a complex number. Nope. Nope. Remember, I'm asking you to plot the probability density. What I've drawn over there is just the real part of the wave function. The wave function has a real part and an imaginary part. No. I'll explain this. A modulus. No. All right. So I have this wave function, this one. Let me now start. This is the wave function. I like to take the modulus squared of this. So what's the modulus squared of this number? It's a squared. Now a can be real itself. A can also be complex. So it's a modulus squared. But a modulus squared is always real. And this is constant. It's independent of x. Independent of time. So my probability density is going to be a straight line. With this wave function, it's a straight line of height a modulus squared. If a itself is real, I don't have to put the modulus sign, but a can also be complex. So it's a uniform probability distribution. Because it's independent of x, it's independent of time. It's a straight line. It's a uniform probability distribution. So if I take y, what do you mean y? Mathematically or physically? Mathematically, if I take any complex number, a, ei theta, I find the modulus squared, which means I'm multiplying this with a star e minus I theta. This cancels out. This is just a star, which is the modulus squared of a. Alright, so just a straight line, independent of x, independent of time. Excuse me, pay attention please. So this is a uniform probability distribution. What this means is that if a particle had this wave function, then I take some region in space, the probability of locating the particle in that region, say, is P1, which is a modulus squared times this weight, because this is probability per unit length. Now I take some other region in space of the same length. The probability of locating the particle inside this region is the same as the probability of locating the particle inside this region. So I take any region whatsoever in space of the same length, the probability of my measurement instrument yielding an outcome within that region is going to be the same. That is what is meant by a uniform probability distribution. And if this wave function, which is really spread out in space, from minus infinity to plus infinity, there's an equal probability of locating it anywhere in space. the wave function can collapse onto any region in space with the same probability density. Yes?
Probability shouldn't be same irrespective of the width of the width which you are taking.
No. So if this is a, suppose this length is delta x. The probability P1 of locating the particle inside this region is A modulus squared delta x, because this is the probability density, the probability for unit length multiplied with the length. Okay, so if I increase the length, the probability of locating the particle inside this region is going to go up. Okay, so it does depend upon the length. The probability density, however, is uniform. Now the question is, we would like all probabilities to sum up to 1. So we're talking about the entire space. The probability of locating the particle somewhere in space is 1. Right? I must locate the particle somewhere in space. So if I were to take a wave function, take the modulus squared, multiply it with dx and take the integral. And my x now goes from minus infinity to plus infinity. Now all of this, you would agree with me, is a probability, right? Because this is probability density, I'm multiplying the probability density with a small length interval, and then I'm summing up over all of space. What should this answer be? 1. Which means that the particle must be located somewhere. कहीं ना कहीं तो होगा particle. जब आप measurement outcome करेंगे, तो you'd be able to locate the particle somewhere in space. Suppose you have a super microscope made by some omnipotent being which can look at all space in one go. Now that particle must land up somewhere in space. So the probability of locating the particle somewhere in space should be 1. That's why when we add up over the entire region in space, our probability must be equal to 1. And this actually helps us find A. This process is called normalization. One last example, and then we'll move on to quantum computing, which actually brings home this idea of normalization. The particle that we've considered here is a free particle. Actually, no such particle exists. Because have you ever thought of a particle that can go from minus infinity to plus infinity? Every system that we are accustomed to dealing with is bounded. It starts somewhere and stops somewhere, either in space or in time. A laser turns on and off. You can never find a laser that has always been on and will always remain on till the day of judgment. I cannot think of such a laser. Or a particle that has moved from minus infinity to plus infinity. It's almost impossible to imagine such a particle. So a free particle is just a mathematical nicety. It just satiates our desire of perfection, nothing else. It's a utopia. The real systems that we deal with are bound systems. For example, suppose I have now suppose I have the following situation. I have x equals 0 and I have x equals L by 2 and minus L by 2. So I have a width in space in one dimension of length capital L. And I have a particle which is doomed or destined to exist only inside this length. So this is like a well. एक कुआं है और एक मेंढक है, वो कुएं के अंदर है और कुएं से बाहर मेंढक नहीं आ सकता. Now these systems can actually be physically made. This is an example of a one-dimensional nanowire, for example. So an electron is confined, is destined to exist inside this well. It cannot go out. Outside this well, the region is forbidden for the electron. So this is a forbidden region for the electron. So the forbidden region is x greater than L by 2. And the other forbidden region is x less than minus L by 2. Inside this well, the electron can exist. So it's a bound particle. It cannot go outside these walls. Now suppose I give you the wave function for this particle. Of course, this particle has a wave function associated with it, a matter wave or a pilot wave or a quantum field, whatever you like to call it. It has some psi associated with it. Suppose the wave function of the particle is given by, has this form. Alright? At some point in time, at some other point in time, it takes up this form. At some other point in time, it takes up this form. At yet some other point in time, it takes up this form. At yet another point in time, it takes up this form. So the end points of this wave function, they are fixed. At the center, the wave function is always 0 at all times. Is this looking familiar? This is called, it's a particular kind of a wave, which is called a standing wave. So this is an example of a standing wave. Okay? So I would like to write down, so this point is called a node, this point is called a node, and so is this point called a node. These points are called antinodes. So this wave function will have a certain mathematical form, and suppose the wave function is real. Okay? And I write down the wave function as a function of x, and at some time the wave function is given by a sine of pi x over L. Suppose this is the wave function at some time t equals 0. Alright? So this means I'm drawing the wave function when it assumes a sine wave. It starts from 0, goes to a maximum value a, then comes down to 0, goes to a minimum value minus a, and then goes to 0. So this is the picture or snapshot of the wave function at some time, and it's real. There's no complex number here. Alright, so the wave function can be real, it can be complex, it can be imaginary. So this is an example of a real wave function. Alright, now what I would like to ask you to draw is, suppose this is my wave function. This is a picture of psi x. Now could you draw a picture of the probability density? What's the probability of locating the particle within a certain regime? For that I would like to plot the probability density function. How does the probability density look like for this wave function? Is this a straight line now? It's not a straight line. It's actually the kind of lobes you were drawing for the previous question, because now this is a real number. The wave function is going to be the modulus squared of this. All of this is a real number. So the square of this is a squared sine squared pi x over L. And it's going to look like this. So this is a picture of small px. The probability density, which is a squared sine squared pi x over L. So just the modulus squared of this function. Now is the probability density uniform? There are certain regions inside this potential well where there is a higher likelihood of finding the electron. You perform a measurement and there is a higher probability that the electron is located over there. So if my region of interest was this region, there is a higher probability, a higher likelihood of finding the electron inside this region. And there is a lower probability comparatively of finding the electron inside this region. And the probability of finding an electron inside a particular region is actually given by the area under the curve of the probability density function. This is what the integral actually means. This is the area under the curve of the probability density function. So there are certain regions inside this well where there are higher likelihood of finding the electron and where there is a lower likelihood of finding the electron. Let me finish, please. Okay? And what's the probability of finding the electron? Somewhere inside the well? 1. So if I take the area under the curve between minus infinity to plus infinity, the answer would be 1. So if I took this probability density function and integrated from minus infinity to plus infinity, now there is 0 probability of finding the electron outside the well. Here the wave function is, what's the wave function in the forbidden region? 0. The wave function in the forbidden region is 0. So this is a complete drawing of the wave function. In the forbidden regions, the wave function is 0. The probability density is 0. So I just need to integrate from minus L by 2 to plus L by 2. A square sine square pi x over L dx. This must give me 1. Now I can perform the integration. It's a definite integral. This will help me find the value of A, the actual value of A. This process is called normalization. One interesting question before I can take up questions from your end. What's the probability of finding the particle at the midpoint of this well? 0. It's 0. I can never find a particle at this point 0. I can never find the particle at the walls of the well. Now this looks something really strange. If you consider the particle to be a classical particle, the electron, if it were a classical particle, It can be found in the left hand of the well, and it can be found in the right region of the well. Suppose this is my well, and this is the node in the center. So I perform I'm an electron. Now, I'm moving inside the well. This is my classical picture. I'm moving inside the well. Sometimes you find the particle to be in the right domain of the well. Sometimes you find me to be in the left domain of the well. But you never find me in the exact center of the well. If I were a classical particle who were actually moving in time, right? In order to cross from the left to the right regime, I have to cross the node. So this is my middle line. This is the midrib of my well. I have to cross this midrib. Therefore, there is a probability or a likelihood that sometimes you should be able to catch me at the center of the well. Alright? That's never going to happen. This means you should stop thinking of the particle as actually a classical particle that is moving around and sometimes capturing the particle in the result of a measurement in the left hand of the well and sometimes the right hand of the well. It's not a particle that is moving around inside the well. It's actually a function, a wave function that is spread out in space. It's everywhere. So in chemistry textbooks, sometimes you draw a p orbital, right? So this is the conventional picture of a p orbital, say a px orbital. Now, you're familiar with these pictures, but what this picture really means? This picture, what does this picture show? This picture actually shows the probability density of the electron in the state px, or an electron that has the wave function px has this probability density. Now this is a naive picture, it's a simplistic picture. ये एक मासूम तस्वीर है, इस पे ज़्यादा ध्यान नहीं देना. Actually, what a better picture would be to draw an electron cloud. And the electron cloud is such that there is a higher density of particles in this upper lobe So this is a more accurate picture, a more realistic picture. Now the density of the dots that I've drawn on the blackboard per unit area represents the probability density, the amount of probability density. Alright? So higher the density of points inside a particular region, higher the density of points, higher would be the likelihood of locating the electron in that region. So this electron cloud actually represents the probability density. And if there were just one electron in the px orbital, suppose there's just one electron, that particular electronic wave function will collapse upon a measurement and will yield just 1 point somewhere in space. It will just yield 1 point. That's the collapse of the Schrödinger cat, the collapse of the wave function. Now if I had another atom in which an identical electron were in a px orbital, I could find that electron at another location. Now if we repeat the experiment on identical copies of electrons in px orbitals and I put all the dots in space, I will get a pattern like this. This is what is meant, how you can interpret electronic orbitals inside the hydrogen atom, for example. Now let's take a 10-minute break and then we'll start off with quantum computing.